So thank you to the Consciousness Club Tokyo for the invitation. It's really good to be here. It's a really, actually I was thinking Consciousness Club Tokyo would be a really good name for a band if I was still doing music. It's a very cool name. So yeah, it's really good to be here and to talk to you about consciousness. I don't know exactly what kind of audience you have. I'm told it's fairly mixed and multidisciplinary background. So I'm hoping that what I talk about today will be of interest to people from a range of backgrounds, because my own approach to this is, as I think Sadira mentioned, is very multidisciplinary. I come from mainly an art background, but I've worked with technology for many years and also worked in science with scientists and using scientific experimentation and so on. So yeah, that's the kind of position I come from on this, and hopefully that will be of interest and relevance to a lot of you. So when I was invited to do this talk, it was on the basis of a paper that I published last year about machine understanding. And I think, yeah, we're all aware that there's been a dramatic change in the world in the last few months. I think 2023 will probably go down in history as the year, as a kind of watershed year in human development, because clearly, you know, something is happening with AI, machine learning. That's clear. It's been around for a long time, but it's changing exponentially as we speak. And yeah, I don't think the world, I'm not alone in saying this, but I don't think the world is ever going to be the same again after this year. I mean, daily, you know, just this morning there were there's news items. I don't know what it's like where you are, but certainly in the UK, there are daily announcements from people warning about the dangers and risks, existential risks actually of AI. How well founded they are, we don't obviously know, but clearly people who experts in the field are very worried. And yeah, who knows where this will go. So it feels like we've entered a new age. I don't know if it's the age of the mechanical mind is one way to think about it. It's very clear, large language models, image generation. I mean, I'm in another life involved in imaging technology, and it's extraordinary what's going on with image generation, for example, which can have an enormous impact in many creative areas, which is kind of one of the areas I work in. So that's clearly happening. And a lot of these systems, whether they understand or not, and we'll come to that, that's largely what I'll talk about, they certainly display, you know, apparent functional evidence of understanding. So, you know, you put in queries and they return, you know, meaningful responses that give the impression at least that they understand what you've asked. So these things are possibly intelligent. They possibly have some understanding. There are different views on that. I was just at the Science of Consciousness conference in Italy last week, and this was a topic many people brought up, and actually quite a few people were saying, you know, don't worry, these things aren't that intelligent. They're quite dumb. You know, they're just statistical machines and so on. So still a big debate about that. And the other thing that's come up is the extent to which they can become conscious, or if they already are conscious. Probably most of you will know or remember that only last year a Google employee was fired for claiming that one of the AIs that they were working on was sentient. Google rebutted that, saying that the claim that it was sentient was wholly unfounded. I think David Chalmers, who did a talk on this topic, said, how did they know? You know, what was the evidence that they had that it was totally unfounded? But anyway, you know, it's clearly become a public debate, and one of some significance. So if you think about human sentience, there's broadly three categories or three areas where we are characteristically sentient. So one is consciousness itself. rather obvious. The other is intelligence. And then the other is understanding, less talked about perhaps, but very important part of our kind of cognitive makeup, the fact that we have this capacity to understand. And clearly these three areas are interrelated. They're not distinct, separate faculties. The extent to which machines have any or all of these faculties is what we're debating. I mean, not just here, but around the world now. As I said, some people claim they have intelligence, some that they have consciousness. A fewer people claim that they are able to understand. But are we gradually shifting from a position where those faculties become clearly embodied in machines and we have machines that are capable of sentience in all these three areas? And perhaps even more challenging is the idea that they could have superior faculties to us in all these three areas. They could be more conscious, more intelligent, and have greater understanding. So again, this is what sort of underlies the debate or the anxiety that we have at the moment about what's going on in the world. I've been thinking about these things for a very long time. I mean, it does seem like a lifetime ago now, but published a book in 1995 called The Post-Human Condition, which was written at the time when microcomputers were first hitting culture. It hadn't been that long before, sort of 10 years or so before, when the Apple Mac had first been launched and the micro PC and so on. And by the mid-90s, it was clear that computers and automated machines and so on were having an enormous impact on our culture and society and our ways of doing things, but we're clearly going to have much more so in the future too. And so this book was kind of an early attempt to come to terms with that. I rewrote it and republished it in the early 2000s. And actually many of the things that I was worrying about at this time were very hypothetical at that point. I mean, the machines were pretty crude compared to what they do today, but nevertheless, you could see the direction of travel and where things were going to go, particularly in terms of consciousness, creativity, and so on, which is largely what I was thinking about. So when I was invited to do this talk, it was on the basis of this paper, which, as I say, was published last year, which came out of a conference I attended a couple of years before on machine understanding. And I was invited to give this talk, and it got me interested in this whole question of whether or not machines can understand and what it means to understand. And for me, it revolved around this question of whether or not such machines would require consciousness. So the outline of the talk today is to think about what understanding is and whether machines can have it. I'm going to argue that in order to understand, certainly in the way that we do, a machine must be conscious in some way. And then I'm going to have a little think about what makes us conscious, and whether we could make machines conscious. And in closing, and very briefly, I'm just going to mention a kind of new approach that I'm working on that may be of interest and relevance to some of you. So understanding, and I have to say that none of this is definitive. This is all work in progress. There are many, many complex issues here, and there's no simple answer or outcome to any of it. But this is a take, or an approach at least, to looking at the problem. So I draw a distinction between three kinds of understanding, which I think it's useful to do. So natural understanding is what we have or recognize in ourselves. I mean, probably other creatures have a similar capacity, but we innately know what it is to understand and what it is for others to understand what we're doing and saying, for example. Then we can think about artificial understanding, which is the kind of understanding that we have now embodied in machines, in large language models, for example. So, as I said before, you can put a query into a large language model, and it will return a intelligible response, which suggests it has some kind of understanding at some level about what was asked. It may just be a statistical model, but nevertheless, functionally, it's working as an kind of understanding. And then the third kind is probably what we don't have yet, which is natural understanding embodied in machines, which can call machine understanding. So this is, something that understands in the same way that we do, or perhaps with even greater capacity than we do, but which is implemented in some kind of other substrate, a mechanical substrate of some kind. And actually the conference that I did the original paper at was trying to investigate to what extent we could move towards machine understanding in the future, for all kinds of practical application reasons mainly. So to try and sort of tease out the differences between those different kinds of understanding, just to give you a couple of examples, understanding is often defined as an ability to grasp or see how different parts or areas relate to one another or depend on one another. So to give you an example, and this is an example from what's called the remote associates test. It's a test of kind of intelligence and creative ability. If you're presented with 3 words, and there's 3 examples there, your task is to find another word that links all 3. I'm just going to give you a couple of seconds to have a think about it. So in each of these cases, there's a word that connects all the 3 words that you can see. It may be a little bit harder for people who don't have English as a first language, but I'll just give you a few seconds just to have a think about it. And I don't know if maybe anyone sees the answer immediately, they can put it in the chat, but have a go. Okay, so I don't know if anyone's got any of the answers, but I'll give them to you here. So the first one is blue, blueprint, blueberry, and bluebird. Fence post, postcard, postmaster, birth control, birthplace, and birth rate. Now, if you can just think back to what was going on in your mind as you were trying to resolve that problem, then there's a few kind of typical steps which most people go through. And if you were really doing it over a longer period, you would go through these steps more intensely. But maybe this describes what you were feeling. So when you had maybe a mild sense of anxiety or discomfort when you're trying to find the answers, the words at first seem unrelated. You take each word in turn and perhaps wait for it to trigger some other thoughts or ideas, other words, almost spontaneously or randomly. Some of those words pop up in your mind, but they're probably wrong and you dismiss them quite quickly. And then if you do find the common word, or when I gave it to you, then suddenly there's some kind of aha moment, a realization, and that changes the meaning of all the other words that the words you were looking at before subtly change their meaning because you now realize they're connected in a way they weren't before with this new word. So in a sense, you're grasping or seeing the connection, yet all the words remain distinct. Even though the words are now connected in a way they weren't before, they still retain their integrity and their separateness. So to give you another example and this is from art history, so this is kind of more my background. I don't know how many people know of these Cubist paintings made by Picasso and Braque in the years just before the First World War. How familiar you are with them. Many people, when they first see these kinds of paintings, think they're completely abstract. They don't realize that they're actually quite precise, clear descriptions of, not clear is the wrong word, but they're full of objects, recognizable objects, normally household objects that become quite visible and tangible when you know how to read the picture. So there's a kind of code in here that once you understand the code or the language, you can recognize what's going on. But for most people, if I say to you, what does this painting depict? You're having a similar kind of struggle to the one that you had just before with the words. You're looking for clues, you're trying to assemble from parts, wholes or coherent objects. It'll make your life a bit easier if I do this. So if I just draw some bounding boxes around some objects here, hopefully that helps you see that there's a glass here, a bowl of fruit, there's a lemon, and a key on the right. There's actually lots of other, yeah. So basically what this is a still life painting of normal household objects on a table. So it's a very, very straightforward scene, but the way the artist has depicted it has made it hard for you to unpack or unpick what the objects are. But having drawn those bounding boxes, hopefully now you can see a bit more clearly how things are laid out. Now, if you go back and look at the original painting without the bounding boxes, you start to be able to make some sense of what it depicts. So in many ways, you go through the same mental processes in viewing that artwork that you did before with the words. As I say, there's probably a mild sense of anxiety or discomfort as you struggle. Things seem unrelated when you first look at them. You're probably trying to pick out individual areas and see if that triggers thoughts or ideas, some of which, you immediately reject because they don't seem to lead anywhere. But when you see the outlines, when I give you some kind of bounding box, then it starts to become clearer, I hope, what those individual shapes are. And again, you start to grasp or see the connections between the parts. Yet when you see the glass and the bowl of fruit, the two things remain distinct, even though they're now connected as being objects in the same scene. So these are examples of understanding, this capacity to grasp or see. And it's been studied, in psychology. It's often referred to as the aha experience, this moment of insight or realization that people have, which can happen very quickly or unfold more slowly over time. It certainly puts you in a new frame of mind when you have this experience. You have a new kind of cognitive or phenomenal state. And it involves actually many kind of sub-processes from recognition, perception, detection, memory, and so on, all of which are related in some way to this kind of broad category that we call understanding. But one way to think about it is that things that were absent become present. Even though you're looking at the same words or the same picture, something is there that wasn't there before. So your mind, your view of the world has changed through this process of understanding. And most importantly, you're able, in doing this, and this is kind of a remarkable capacity that we have, to hold many distinct concepts in your mind whilst also seeing how they are also related to one another at the same time. And this is a theme I'm going to come back to because it's really important both for understanding and understanding consciousness and thinking about how we might implement it in machines. So this cartoon from Saul Steinberg was on the front of the New Yorker magazine many years ago, and it kind of illustrates this process that we've been talking about. So it shows somebody looking at a Cubist painting by Braque in a museum, and it's illustrated the kind of cloud of thoughts, the diverse ideas or suggestions that the painting generates in somebody's mind. And I've certainly experienced this myself, looking at these paintings and other kinds of paintings too. You go through this process of assimilating lots of different potential ideas. And this really is a kind of reflection of our cognitive state during the process of understanding. Now, what's interesting about this, or one of the interesting things, is that it needn't be consistent or logical. Many of these ideas can be even contradictory to one another. So to give you an example here, just to go back and look at the painting, that little patch in the square in the middle there, it represents a lemon. When you look at that, you hopefully understand that it's a lemon. I mean, it has a kind of vaguely lemon-like shape to it, which you can see and appreciate and understand. But at the same time, it's clearly not a lemon. It's also a patch of paint. And somehow in our minds, we're able to reconcile this incompatible or contradictory information. We can see it both as a lemon and both as a patch of paint. And this seems to be a crucial aspect of our capacity to understand, to be able to hold these distinct ideas in our minds at the same time. So these are some of the key properties of natural understanding. It's not an exhaustive list, but it does capture, a lot of what I've been describing. We have this capacity of insight. We're able to learn, recognize, and so on. But there's two or three I want to really draw your attention to here. And these, I think, are critical to what we're going to discuss next in relation to consciousness more generally. So natural understanding clearly gives us this capacity to differentiate, that is, to separate things in perceptual space or cognitive space, whilst at the same time being able to integrate them into some kind of whole or some kind of meaningful entirety. And then the other important aspect of this is all happening in consciousness. So while a lot of the underlying cognitive processes will be unconscious, most of what goes on in our minds cognitively happens unconsciously. But the moment of realization, the sense of grasping, the sense of unification, and so on, that occurs to us in our conscious awareness. We are phenomenologically aware of that going on, which is an important point, again, we'll come back to. Okay, so the second kind of understanding mentioned earlier on is artificial understanding. And this is the kind, as I said, that we have already implemented in things like neural networks. These have evolved, of course, from early brain-inspired models, the Pandemonium, for example, and Perceptron of the late 1950s. They functioned by having some kind of detector input that could distinguish or separate or divide up the input data. And then they would integrate that using some kind of weighting measure, summing the weightings and then producing an output which was the most likely the likely output given the input data, which led, of course, to the parallel distributed processes of the 1980s, and then ultimately onto the kind of machine learning techniques that we have today. I'm not going to go into these in detail, but I just want to point out that actually a similar kind of process is going on here, even in these very simple early neural network architectures, that kind of reflects what I've just been talking about in terms of the process of differentiating and integrating. So, as I just said, these architectures often just kind of break up the world into discrete chunks. They then add weights to the different chunks based on probabilistic measures, and then they integrate those somehow to provide an output. And much the same thing is going on in well, it certainly was until recently. I don't know if this is still how it's done, but image classification systems would work very much in the same way by dividing the image up into chunks or blocks or pixels and statistically estimating the likelihood of of the arrangements being a certain way to give you a certain output. And so the net result was, and the research I was looking at around 2020-21, showed that the machines were really good at this. They were able to draw bounding boxes around objects and label them with a high degree of reliability. Much in the same way, that we just did with the cubist picture, although this would have been a much harder task, obviously, for a machine classifier. So, as I'm sure most of you know, or all of you know, that the techniques that have been evolving to carry out these kinds of tasks, so image classification, for example, natural language processing, have been evolving rapidly since around 2012. In 2012, the AlexNet was getting a score of around 63%, and then by 2021, that had gone up to 90%, and I'm sure it's higher now. And performance in language models is very, very good. In some ways exceeds human performance, and what it's doing with image generation, Midjourney, and so on is clearly extraordinary as well. So we have some sense of artificial understanding being embodied in machines. Machines seem to kind of understand something about what we're asking them to do and how they need to respond. And we can again tabulate the key features of this artificial understanding, which largely overlap with those of natural understanding. There's only a few differences I'll come back to in a second, but they are quite critical differences. But again, a key property of artificial understanding is that it has this capacity for differentiation and integration. Now, again, when I was looking into the kind of background research, writing this paper up, and this was only a couple of years ago, there was still quite a big debate going on in the community about the extent to which this kind of artificial understanding was really understanding or was really adequate for the task that it was being asked to do. So clearly performance was improving very quickly, but questions remained about, is this really a kind of understanding? I mean, this goes back to John Searle's argument from the mid-1980s about the Chinese room. If something is just kind of syntactically matching symbols in a way that it has no intrinsic understanding about, in order to give the correct answer, someone seeing that process from the outside would get the impression that that process has an understanding, but in itself it doesn't. It's just simply matching up codes or clues. This actually goes back even further into history. There was the Clever Hans argument. Clever Hans was a horse who was apparently able to do quite complex mathematics around the early part of the 20th century, I think, was apparently able to respond to complex questions about mathematics and able to do calculations in a very convincing way. It turned out that it was really just responding to some very subtle body cues from its trainer. So the understanding it seemed to have was not of the kind that people thought from its behavior. And certainly quite recently, people were saying that AIs are still brittle, they're non-generalizable, and they struggle with ambiguous cues. Sorry, no, I'll come to that in a second. That there's a danger of shallow learning because they're limited to their training sets, and yes, they struggle with hard cases. So the cubist painting I showed you earlier would have been a very difficult challenge unless it had been trained on lots and lots of cubist paintings. So this idea that the intelligence is limited only to the cases it's trained on, it doesn't have this capacity for generalizability and ability to deal with new, novel, and ambiguous examples. Now, again, things have moved on very, very rapidly in the last 6 months to a year. So I don't know where the current thinking on this question is. But we can certainly, we can compare artificial and natural understanding quite favorably, even on the basis of where things were a year or so ago. Many of the faculties that we would think constitute understanding are shared by both natural and artificial systems. But the key differences, I'm arguing, are there are not many of them, but they're very, very important. The main one actually being the capacity for consciousness. Now, as far as we know, there are no machines that do have capacity for sentience or consciousness. In many ways, they may not need it. A lot of people argue that as long as a machine works, does its job, does what you ask it to do, then it's not necessary at all that it should be conscious. This has been quite an important strand in thinking in machine understanding literature. But I'm going to suggest that it is. And by consciousness, I mean very simply in this case, awareness of self and environment. I mean, we could get into that a lot more, but I think that's a useful starting definition. And we're learning an enormous amount very, very quickly about how the brain, how neural activity is associated with conscious experience. I mean, the growth in knowledge of that in that field, which I've been following for a number of years, is also growing exponentially. The number of theories about how the brain produces consciousness is also expanding exponentially. I mean, there's, I think, I can't remember last count, there's well over 30, I think in one paper cited 30 current theories. So we're not short of theories about how this might work. We've got lots of evidence from neuroscientific studies and so on. Two of the largest or most widely discussed theories, integrated information and global workspace theory, are now claimed to be well supported with evidence. And actually, even though they're quite different theories in many, many ways, as you know, all the different theories have their differences with each other, but in fact, in a fundamental way, they're quite similar, because both IIT and GWT in different ways suggest that what distinguishes a conscious brain or activity in a conscious brain from one that's not conscious is the kind or the complexity of the neural activity that's going on inside it. In fact, more specifically, we can say it's the amount of simultaneous differentiation and integration that's going on in the neural activity that differentiates conscious from unconscious brains. So, yeah, just to, I'm not going to go into this in depth, but just to illustrate this from a couple of well-known diagrams that are often published, you know, to support the ideas of these theories. The global workspace theory, I'm sure a lot of you know about it. Basically, it's this idea that you have this distributed network of distinct cognitive processes that are embodied in the brain in various different areas, and that they kind of can all go on independently, more or less independently of one another, in an unconscious state, whether that's sensory processing or memory or whatever it might be. And then when the global workspace kicks in, it somehow brings all those kind of different parts together by broadcasting something that integrates them into a whole. So it's a very similar idea to what we were talking about before, which is lots of different things independently situated and activated, somehow at one moment coming together as a coherent whole without losing their local identity. That's the important thing. And a very similar idea actually underpins IIT as well. IIT has this core idea about how the brain, both what they call it information, but has these discrete differentiated parts, and then providing it has enough integration between those parts of the right kind, indivisible, then it reaches this threshold for consciousness. So there's, broadly speaking, there's a kind of correspondence between these theories in that respect as well, even though in many other respects they're quite different. And it's not that recent now, it's 10 years old, but a piece of empirical evidence that was thought to be very supportive of the IIT approach, and has since actually been replicated many times in many different ways, shows that it is the kind of structural organization or the dynamical organization of the neural activity that differentiates, conscious from unconscious states. So, I mean, probably a lot of you know this study, or others like it. Basically, what happened is, people who had different levels of consciousness, so like fully awake, healthy people versus people with impaired consciousness, a magnetic pulse was put through their brain. It was stimulated with a magnetic pulse. The kind of echo of that pulse through the neural tissue was recorded, or the neural activity that was stimulated by that pulse was recorded with EEG. And then the images of the EEG were basically analyzed in terms of how compressible they were, using a relatively simple, as I understand it, compression algorithm. And effectively what they found was that the more compressible the image of the brain response to the stimulation, the more unconscious somebody was. The more complex and uncompressible that image, then the more likely someone was to be conscious. And you can see that plotted in the graph on the right. There's quite a simple idea that actually the complexity measured by compressibility of brain activity is a signature of level of consciousness. And this turns out to be a pretty reliable indicator. It's been used many, many times and replicated in many different ways. And the authors say much as what I've been saying earlier, which is consciousness depends on the brain's ability to support complex. Sorry, 1 second. I can't actually see, but yeah. Patterns that are once distributed amongst interacting cortical areas that are integrated and differentiated in space and time. In other words, they're information rich. So it's this idea again of something that's both differentiated and integrated at the same time, being the signature or the primary characteristic of a consciously experienced system. Now, it's an interesting question here about what this PCI, this perturbation complexity index, what it's actually an index of. I mean, in most of the literature about it, people argue that it's an index of information processing complexity. This is generally the most widely held view, and this is based on the idea, which is very commonly held, that the brain is really a kind of information processing computer that's running on a sort of binary code that's implemented with neural spikes. And this is a very convenient and attractive way to think about what the brain is and what it's doing. I can certainly see why you'd think about it in that way and what the advantages of thinking about it in that way would be. But I also think there are limitations in thinking about the brain in that way and its processing, which I won't go into now, but they're discussed elsewhere. I can direct you to the papers. What I actually think is going on is this is an index of the brain's energy processing complexity. This is quite a different thing. This treats the brain not as an information processing machine, but as a system that's churning over energy in order to harness that energy to carry out tasks that benefit the organism. So it's a very high level description of what I mean there. But essentially what it does is it puts the emphasis on understanding brain process and brain structure and function on the energetic activity that it's undergoing, metabolic and so on. It's just a different way of looking at the brain process and brain activity, and a different way of interpreting that kind of information or that kind of data that we get from those brain studies. And so in that case, and treating the brain in that way, the PCI is measuring the complexity of the organization of the energy in the brain rather than the information. And that may feel a little bit like splitting hairs because, yeah, of course, one could argue that you need energy to do the information processing, but I actually think it's more important than that and more fundamental than that. And I'll try and explain why shortly. In fact, this paper here sort of sets out the argument in more detail, if you're interested. So hopefully what's starting to become clear, if we just think back to those early examples I showed you of understanding connections between words, or understanding objects sitting within an image. This idea of grasping or seeing lots of different things at the same time and their connections. This seems to have a relationship to consciousness more widely, our general capacity for being conscious. And because they both are highly differentiated and highly integrated. And in some ways, the more they are, the more differentiated and integrated they are, the more we understand, and also the more conscious we become. And this seems to be both phenomenologically the case by introspecting on our own experience and thinking what it's like to understand something or to be aware of something. But it's also clearly, a key way of empirically monitoring or modeling what's going on in the brain that underpins neurologically that conscious experience. And this little picture illustrates that process. This is actually from a paper I'm working on at the moment, on the same idea, but it just illustrates, the transition from what's in box A there is a differentiated system. So the little green dots there show that there's activity in the system, but none of the active areas are in any way connected to one another. And so you can see in the little graph and in the bottom right there, the level of differentiation and integration is very low. And then gradually, as the boxes proceed, A, B, C, and so on, you can see that the areas of activity start to hook up with one another. They start to inference or integrate to one another. By the time you get to box E, you've exceeded a threshold of differentiation integration such that the system has become consciously aware, which is indicated by a little meter on the left there. And then in box F, you've a very high level of activity, which is very complexly integrated and interactive. And then you've kind of got into some kind of heightened or greater conscious state than you would have been in box E, on case E. So it's just a very simplistic illustration of this idea of how integration and differentiation can evolve over time and in different ways and systems to underpin different levels of conscious experience. Just a couple of other points to make on the difference between natural and artificial understanding, which are also important to mention. One is insight. Again, going back to this idea of aha. Many people have studied this in humans, and I think to some extent in animals as well. And it's largely thought that this kind of aha experience, this moment of realization, is really important, again, for integrating different brain processes. So these are people who are not studying consciousness per se. They're studying more cognitive processing in task performance and so on. But they recognize that these kinds of realization experiences, where we grasp many things at the same time, do actually have a neurological correlate in the way that different brain processes are integrated. And we see this in many different studies where widely distributed brain processes become bound together during this moment of realization or insight. Other work has shown that the moment of insight is actually the culmination or the endpoint of a lot of prior processes that are occurring independently but simultaneously, that then gradually build up to this this kind of instant moment of realization. And so some authors have said it's drawing together these unconscious states into a single conscious state of mind. And then another very important aspect of understanding is the fact that it feels rewarding to have a realization. So studies have shown that people who have experienced insight, and it's not particularly surprising, but it has been shown empirically, have positively valent states, which feel to them rich. They feel calm, happy. They feel more certain about the world and themselves. So generally, it's a positive feeling which people have in response to these moments of insight or understanding. Other studies have shown that when people solve problems, that reinforces other cognitive processes like memory. It reorganizes their capacity to make sense of things. It improves speed of retrieval for information from the mind and so on. And of course, it's highly motivating that when we have or seek solutions to problems, we do so because we are trying to gain the reward at the end of that seeking task. So that gives us an incentive or reason to put the work or the effort in to trying to solve the problem. And again, that's thought to be related to underlying processes of integration, of differentiation in the cognitive system. So to try and pull all that together, when we understand something, this is really the kind of point of the argument I'm trying to make, when we try and understand something, or when we do understand something, this moment is characterized by high degrees of simultaneous differentiation and integration. And that's occurring both neurobiologically on the basis of what we can measure in terms of brain activity at various levels, and it's occurring phenomenologically. If we introspect on what it's like to understand something or have a moment of insight, it feels like it's made of lots of different things coming together or being grasped at the same time. And along with that goes a positive emotional feeling, a positive valence that rewards the effort that we've put in to try and to solve that problem. And that in turn motivates us to carry on doing the same thing in the future, because we know that in solving a problem, we will get this positive feeling of reward. So all those complex kind of psychological, cognitive, emotional processes all seem to be bound up together in some complex way in this process of understanding that we all go through in different ways. So this thinking and this evidence really led to the core hypothesis that was proposed in the paper, which tries to explain, or at least may put us on the right track to explaining why we understand and what it might take to get a machine to understand in the same way that we do. And what that means is not just being able to respond more or less accurately to a command or an input, but that it's able to do that with the same robustness that we are. It's able to generalize from cases that it hasn't seen before, able to deal with hard cases. And perhaps the most difficult thing is that it authentically appreciates or has some sense of meaning about what it's understanding. And this is probably the trickiest thing to analyze, because it touches on questions about consciousness and so on, which we know are very difficult anyway. But if we were able to endow a machine with those kinds of capacities, then it would do so because it's motivated to gain the insight. So the motivation to solve the problem has to be an intrinsic part of that process. In doing so, it will have unified lots of divergent concepts through the process of insight, and it would have somehow had a reward from doing that process and achieving the state of understanding. So understanding is not just about information processing, it's also about motivation, reward, emotion, and so on. All these things are bound together. And really, the argument would be that we need to endow a machine with some capacity for all those things if it is to successfully understand in the way that we do. So this hypothesis suggests two ways in which understanding in us is working, natural understanding. Firstly, that it's promising reward and the positive states of emotion that go with that. That's giving us intrinsic motivation to act, to put the effort in to trying to solve the problem. That means giving cognitive resources, which are expensive, that costs energy and time, which we could be using elsewhere. But it gives us those capacities to recognize objects, to search for things and find them, and so on. So understanding is a process, as I say, of many, many things going on simultaneously that are all organized towards the end of achieving insight, which is then rewarded with a positive emotional state. And the underlying neurobiological activity that is allowing all this to happen, presumably at some fundamental level in the brain, is probably occurring because it has sufficient degrees of differentiation and integration going on simultaneously. However, that is instantiated in the brain architecture itself. And there are many, many different ways that could be done, given the complexity of the brain. This underlying neurological activity seems to also be reflected in phenomenology that goes along with these experiences. This idea of simultaneously grasping many different things at the same time, even though quite often those things can be completely contradictory. They may have no obvious relationship to each other. They may actually be completely incompatible with one another, yet nevertheless they do actually make some kind of sense when held together in the mind. And so to try and to put all this into a machine, to try and build a machine that has this capacity is clearly going to be extremely challenging. But the approach that I would suggest would be a naturalistic one. And actually, this is the approach that I've taken in other similar kinds of problems. In other words, to look at how the system we're modeling does it, in this case, us, the human mind, the human brain, and then to try and model our solution on that as closely as possible, both phenomenologically and in engineering terms. So that means, for example, how does the brain generate consciousness, insight, reward, and understanding? Yeah, we don't know the answer to that, but that would be where we need to start looking. And then that raises the whole question about whether or not the brain is really a digital computer, or is it some kind of energy processing system that's using the motive power of energy to drive its processes and its behaviors. And again, I've already said that where I stand on that topic, it's an open question. But my argument would be, if we want a naturalistic kind of understanding machine, then it's going to at least have to take into account this energy processing aspect to our neurobiology. Now, the whole question of energy is really important, not just on a conceptual level, but actually on a very practical level. I mean, what's extraordinary about the human brain is how energy efficient it is, and how it, given if you want to think about it in these terms, the computational power it has relative to its energy demands, it is extraordinarily high. So, I mean, it's a well-known, you see this cited in lots of places, that even though the human brain is only around 2% of the body mass, it consumes around about 20% of the energy budget when at rest. So that's a very, very high energy demand for a single organ in the human body. So this suggests that the brain is incredibly energy hungry, but it's not because it's energy inefficient. There are people who have calculated the computational rate of the brain versus that of computers, and in whatever way you measure it, the brain is just vastly more efficient computationally than any current computer system that we have. I mean, there's a couple of examples of calculations there. I mean, I'm not alone in saying this. A number of people have argued that we do need to take the role of energy in the brain much more seriously. Again, I've argued it myself. And as I've said, a lot of the contemporary neuroscientific data that we have about how brain processes underpin conscious processes can be interpreted totally, rationally in terms of energetic flow as much as in terms of information flow. So there's not necessarily an inconsistency between those two views. They're just two different ways of looking at the same data. But when it comes to actually designing machines, the capacity, the energy demands are almost certainly going to be a limitation on performance. So people have recognized this for a long time. We're already kind of pushing very hard on our energy resources in driving a lot of our machine learning systems. People are aware of that too. And so attempts are being made, serious attempts to try to come up with ways of designing, for example, neuromorphic hardware that is far more energy efficient than the current ways of doing computation that we have at the moment. And this is a growing area of interest, and it's driven a lot by awareness of the environmental impact of our current, for example, our GPUs, which are very, very energy intense. And yeah, and this, I mean, there's lots of different, I mean, a lot of you probably know more about this than me, but there's lots of different kind of non-conventional computing methods being investigated that bring us closer, or bring the architecture of the computational device closer to that of the human brain. Of course, the original perceptron and pandemonium devices and the parallel architecture machines. In fact, the very word neural network suggests that we're always looking to the brain and neural structures to inspire our computational designs. And in some ways, this is just a continuation of that process. But I think, having understood that there's this interesting kind of interplay between, is the brain a computer? If so, we need to we need to think about the brain in computational terms, or is the brain something else, in which case our computers need to be modeled around that? It's a very interesting and complex debate. But certainly, there's a lot of work going on that suggests that we're moving away from the kind of rigid binary processing systems and machines that we've relied on to date. The final thing I want to mention, just in closing, is related to this. I'm not going to go into this in detail, but my own view, having kind of looked at this from various different angles, is that all this suggests that we need some kind of new approach to thinking about how consciousness is instantiated or generated by brain processes, physical processes more generally, and how this might affect our understanding of how they might be produced in machines. Of course, I'm not alone in this. A lot of people say exactly the same thing. Having just been at the Towards the Science of Consciousness conference last week, a lot of talks, a lot of people saying, this is what I think. This is there's no shortage of ideas, but we're clearly still some way away from a core theory of consciousness that everyone can get around and start working on. It's a very, very disparate and diverse field. And so, many people said actually at the conference, we desperately need some kind of coherent theory to draw all this together. Now, I'm obviously not going to give you that now, but I'm going to suggest that that following some of the ideas I've presented to you here today, there are some very interesting possibilities that would be worth investigating. And there's one in particular that I've been working on for the last 4 or 5 years, which the key feature of which is that it takes experience to be a property of matter. And I'm not going to go into this now, but just to say that it is a physically based theory that could potentially explain why certain neurological processes produce experience, as well as how. And importantly, it's testifiable, falsifiable, and generates predictions. It's consistent with empirical findings in neuroscience, and also with many historical examples, which I've been looking at recently, going back to the 19th century as well, from philosophers and scientists. So there's a couple of draft papers available if anyone's interested in this. But the reason I'm actually raising it today, and I don't know much about the community here, but I'm very interested in anyone who might want to collaborate in this area, because there are certainly skills that would be useful to bring to this that I don't have myself. And it's actually very, very simple. It's just looking at how energy circulates through complex systems. They don't even have to be that complex. So the idea is that if you can measure the transfer of energy between portions of matter, so, for example, in very simple systems like these, then you can measure the transfer of experience through the system and start to build models of how material systems have experiences and generate more complex experiences from their underlying physical activity. So if anyone's interested in this, and I've given a very, very brief and garbled probably introduction to it, but if anyone's interested in this and is perhaps interested in modeling some of these quantities in real systems, I'd be really interested to hear from you and talk about if there's anything we could do together. So I just want to close by saying that quite a few people have recently expressed regret about some of the work they've been doing in artificial intelligence over the years. There was a news piece this morning about exactly that, because of the enormous threat that it seems to pose to humans more generally in the future. And I have to admit that, I'm thinking something similar myself. I'm having worked on or thought about machine consciousness for many years now, since the 1990s, and always having felt that it would be a good thing in general that we could design machines that were conscious. And particularly with the stuff I'm doing at the moment, which, at least in theory, would start to give you a physical mechanism through which to produce consciousness in mechanical devices. There's huge advantages to that potentially. I mean, the one that actually I'm most interested in is understanding what the nature of pain and pleasure and how that's implemented in physical systems. And clearly that would have huge clinical benefits and therapeutic benefits. But I'm very aware that exactly the same kind of understanding of how physical nature generates things like emotions, feelings, and pain could equally well lead to negative and perhaps even horrific consequences if it were to be mishandled. So, I'm myself very conscious of the kind of ethical dilemma as we move towards the possibility of conscious machines, which I think is certainly something many people are working on. Like many technologies, it has both very, very positive potential benefits, but also very very unpleasant ones. And I think it's just it's very salutary to think about that dilemma at this time, when we have this ability to make such great progress at the same time as to wreak such destruction. So just to conclude, my argument is that natural understanding entails high degrees of differentiation and integration, and both phenomenologically and neurobiologically. Consciousness seems to be a requirement for natural understanding. I don't think you can understand in the way we do without being conscious of the fact you're doing it. And it does this because it enhances a lot of other things that go on in our minds. We gain insight, we get reward, we're motivated, our memories are expanded, and so on. When we look at the underpinnings of our phenomenology in neuroscience, we find a correlation here between high degrees of differentiation and integration that seem to be required for conscious activity to occur at all. And if we are going to model understanding in machines in any way that's like ourselves, then we need to do it on the basis of natural understanding rather than the artificial kind that we currently have today. And that's it. Thank you very much.